Hello everyone, welcome to my channel. This is educational channel doing educational material, usually of the obscure and esoteric variety, things that people don't know anything about unless they've been doing a lot of digging, and but things I think are useful for people to understand and have that perspective. Today is, I believe, our 195th video that we've done on the reciprocal system of theory. And this is a theory that was first derived by Dewey B. Larson back in the 20th century. It's a theory of everything that he applied to many, many different subjects, including physics and chemistry and economics, astronomy and astrophysics, and psychology and religion and philosophy, and his followers have also applied it to many other subjects in addition to that. And so it's a basic kind of template. He has two fundamental postulates, and then he takes those two fundamental postulates, and through a process of deduction, he derives an entire theoretical universe from those postulates, and then compares his universe with the universe that the scientists have come up with through their observations and measurements. And we are looking at his 1979 book that's called Nothing But Motion. The basic gist of the reciprocal system is that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy, it's made out of motion. And other people have posited that before, but what distinguishes Larson's universe of motion is that motion he defines specifically as the relationship between space and time. That sets up a generalized reciprocal relationship between space and time, hence the reciprocal system of theory, as the name of his theory. And it also sets up a few other relationships that space and time have together. Basically, space and time are identical to one another except that they are reciprocals. Neither space nor time actually exist. They only exist together in motion. Larson sometimes uses this box analogy to describe this. If you have a box, then you ought to, the box basically representing motion. If you have a box, then you automatically have an inside and an outside of the box. The outside of the box is space, and the inside of the box is time. And if you don't have a box, you don't have either an inside or outside. So it's kind of like they come in threesomes. You know, if you don't have a box, then you don't have anything. If you have the box, then you automatically have all three: the box, the inside, and the outside. And what that eventually maps out to is the box is unit motion, and it is the boundary between this outside region, which is space, and this inside region, which is time. That's just an analogy, not completely exact, but it's pretty simple to think of it that way. Now, space and time have really three things that Larson talks about in his postulates that coincide. They both have their coordinate aspects, meaning that they both come in three or more dimensions, x, y, z coordinates. We recognize that in space. We recognize that space is three-dimensional. But we generally don't recognize that time is three-dimensional, or three or more dimensions. It has x, y, z coordinates. And then we also, time and space also both have what Larson calls the clock aspect, or scalar, one-dimensional scalar motion. Time, we recognize that time follows the clock. Time is always getting later and later and later. And this is a one-dimensional scalar motion. A scalar motion is a motion that has a magnitude, but it has no direction. You can envision this by using a balloon and putting a bunch of dots on the balloon with a magic marker. If you blow up the balloon, all of the dots are moving away from each other. That is an outward scalar motion. If you suck in the balloon, all the dots are moving toward each other, but in no particular direction. And that is an inward scalar motion. And so too, space also has its clock aspect. Space is always getting farther and farther and farther apart. And just like the balloon analogy, this was actually discovered almost 100 years ago by the Hubble telescope, that observed that all of the distant galaxies are moving away from each other. A scalar motion, kind of like the distant galaxies are on the surface of this balloon. Then also, time and space both have their discrete units. They only come in discrete units. There is no continuity of space and time. They come in chunks. There is a minimum unit of space and a minimum unit of time. Less than a unit of space, you have no space. You only have time. Less than a unit of time, you have no time. You only have space. And so, if you have 1 unit of space in 1 unit of time, then you have the speed of light. So the speed of light represents a boundary in between 2 separate universes, or sectors of the universe, as Larson calls them, the material sector and the cosmic sector. The material sector is everything that's moving slower than the speed of light. This is the sector that we're familiar with, and this is the sector where we have our coordinate space and our clock time. But there is also another half of the universe that we know very little to nothing about. Larson calls this the cosmic sector of the universe. And in this universe, there is coordinate time, 3-dimensional time, and clock space, progressing space where space is getting later and later and later. And in between those two, we have that boundary, the speed of light. And then the other 2 boundaries of the universe are the unit boundaries, a unit of space and a unit of time. So within the material sector, the sector moving slower than the speed of light, we have what is called the time region. That's where you are within a unit of space. Within a unit of space, you don't have space, you only have time. And so that is what's called the time region. And in the same way, on the other side of the boundary, in the cosmic sector, you have the space region. Within a unit of time, there is no time, there is only space. And what you see with this reciprocal relationship is that even though we don't really understand anything about the cosmic sector, we do understand the material sector from our observations and measurements and our scientific so-called progress. And so all we have to do is extrapolate from what is in the material sector is exactly the same as what's in the cosmic sector, except that the roles of space and time are reversed. Now, Larson will get into this general idea here in chapter 14 of this book, Nothing But Motion. This book is primarily on atomic physics, but this chapter 14 is called Cosmic Elements. So just like in the material sector where we have the elements, we have hydrogen, and we have oxygen, and we have nitrogen, and we have carbon, we have helium, all of these elements of the periodic table. Well, in the cosmic sector, there are the counterpart of the material elements, and Larson calls these the cosmic elements. And so he's going to get into explain, and the difference between them is that you invert the relationship of space and time. You invert the roles of space and time. And so Larson is going to get into discussing what a cosmic element is, and using this extrapolation process and determining what is a cosmic element. Okay, so we're going to start right here with Larson in his own words. As pointed out in chapter 6, the inversion of space and time in physical phenomena that is possible by reason of the reciprocal relation between the 2 entities may apply to only one of the constituent motions of a complex physical entity or phenomena, or it may apply to the entire structure. We have already examined some of the effects of inversion of single motion components, such as translational motion in time, negative displacement in the electric dimension of the atomic rotation, etc. Now we are ready to take a look at the consequences of complete inversions. It has already been noted that the rotational combinations which constitute the atoms and subatomic particles of the material system are photons vibrating in time and rotating in space, and that they are paralleled by a similar system of combinations in which the photons are vibrating in space and rotating in time. The point to be emphasized at this juncture is that the inverse system, the cosmic system of atoms and subatomic particles, is identical with the material system in every respect, except for the space-time inversion. Corresponding to carbon 2-1-4. Now remember, those three numbers that's Larson's notation for each element. The first number represents the primary two-dimensional rotation. The second number is the secondary two-dimensional rotation. And the third number is the one-dimensional rotation. Okay, so when you say 2-1-4, that's what you're meaning. Two primary two-dimensional, two secondary two-dimensional, and four one-dimensional. Okay, so corresponding to carbon 2-1-4, there is cosmic carbon -2-1-4. Corresponding to the neutrino M 1/2-1/2-1, there is the cosmic neutrino C -1/2-1/2-1, and so on. Now the M and the C that are placed before those numbers only apply to subatomic particles, and they represent kind of like the base on which you're building. So in the first instance, the M represents material and the C represents cosmic. So you're building upon this material base, and in the cosmic neutrino, you're building on this cosmic base. Furthermore, this identity applies with equal force to all of the entities and phenomena of the physical universe. Since everything that exists in the material sector of the universe is a manifestation of motion, every item is exactly duplicated in the cosmic sector with space and time interchanged. The detailed description of the material sector of the universe that we are deriving item by item through development of the consequences of the basic postulates of the reciprocal system of theory is therefore equally applicable to the cosmic sector. Thus, even though the cosmic sector is almost entirely unobservable, we have just as exact and just as detailed knowledge of that sector, aside from information about specific individuals of the various classes of objects, as we do of the material sector. It should be noted, however, that our knowledge of the material sector is knowledge of how the phenomena of that sector appear to observation from a point within that sector, that is, a location in a gravitationally bound system. What we know about the cosmic sector through application of the reciprocal relation is knowledge of the same kind. Information as to how the phenomena of the cosmic sector appear to observation from a location within that sector. A location is a system that is gravitationally bound in time. Such knowledge has no direct significance from our standpoint, as we cannot make observations from such a base, but it does provide a basis from which we can determine how the phenomena of the cosmic sector and the phenomena originating in that sector theoretically should appear to our observation. So we know what these things in the cosmic sector would look like if we were in the cosmic sector, but we are not. And so we have to use certain, what he calls like translational mechanisms, translational devices to be able to translate what is actually in the cosmic sector to what we actually would see from our vantage point. There is a what Larson calls interregional ratio. There's a translation. There's a certain amount of information that's going to be kind of lost in the translation from one sector to another. So we know what the cosmic sector would look like if we were in it, but we're not. And so we have to kind of reduce the measurement of what we would see to what we actually are seeing. As one of Larson's followers, Bruce Perret, had said, we see space, but we do not see time. We only see time as it affects space. And it affects space in a generally an inverse manner. So an example is the white dwarf star. A white dwarf star is an explosion that goes across the boundary to faster than light speed, so into the cosmic sector. And so we see an exploding star, but once it crosses the speed of light, it starts to explode in time instead of in space. But we don't see time, we only see space. So what we actually see is the inverse of an explosion in time, which is actually an implosion in space. So we see a white dwarf star as a dwarf, as a very small and very dense star. So that is kind of what he's talking about there, where that's not what's actually happening. What's actually happening is that the star is exploding in time. But since we don't see time, we only see space, we see it as an implosion in space, the reciprocal relationship. Okay, one of the most perplexing questions of present-day physics is, where is the antimatter? Considerations of symmetry applied to the current theories of the structure of matter indicate that there should be antiforms of the elements of which ordinary matter is constituted, and that the antimatter composed of those anti-elements ought to be equally as abundant in the universe as a whole as ordinary matter. Anti-stars and anti-galaxies should theoretically be as plentiful as ordinary stars and ordinary galaxies, but there is no hard evidence of the existence of any such objects. It has been suggested, to be sure, that some of the observed galaxies may be composed of antimatter. Alfvén, for example, says that there is a, quote, distinct possibility that anti-worlds may actually be neighbors of ours, astronomically speaking. It cannot be excluded that the Andromeda Nebula, the closest galaxy to ours, or even stars within our own galaxies are composed of antimatter, end quote. But this is pure speculation. In the absence of any demonstrated means of distinguishing the radiation produced by a galaxy of the hypothetical antimatter from that produced by a galaxy of ordinary matter. So the question remains, where is the antimatter? The reciprocal system now provides the answer. This new structure of theory agrees that antimatter, actually reciprocal matter, cosmic matter as we are calling it, exists, and that it is equally as abundant in the physical universe as ordinary matter. But it tells us that the galaxies of cosmic matter are not localized in space, they are localized in three-dimensional time. The progression of time to which we are subject carries us through this three-dimensional time in a manner analogous to a linear motion through three-dimensional space. Only a very small fraction of the total number of objects occupying positions in the spatial reference system would be encountered in the course of a one-dimensional spatial motion of this kind. And the same is true of the number of cosmic objects that are encountered in our progression through time, is compared with the total, I think it should be as compared with the total number of such objects occupying positions in a three-dimensional temporal reference system. Furthermore, gravitation in the cosmic sector acts in time rather than in space, and the atoms of which a cosmic aggregate is composed are contiguous in time, but widely dispersed in space. Thus, even the relatively small number of cosmic aggregates that we do encounter in our movement through time are not encountered as spatial aggregates. They are encountered as individual atoms widely dispersed in space. We cannot recognize a cosmic star or galaxy because we observe it only one atom at a time. Radiation from the cosmic sector